Hello everyone, I am Himanshu Kumar. Today along with my team member will discuss the topic pruning in multiplayer game tree. We are thankful to Dr. Arijit Mondal for his guidance and support. Let's begin. First, let us discuss the introduction and overview part. Much work and attention has been focused on two-player games and alpha, beta, min-max search. Alpha beta pruning works particularly well on games of two players or games with two teams, such as bridge. Much less work has been focused on games with three or more teams or players, such as hearts. We first review the Maxent algorithm and condition under which pruning can be applied to Maxent. Based on this, we show that shallow pruning in Maxent cannot occur in many multiplayer games. We will examine another common pruning method, branch and bound pruning, showing that it faces the same limitation as alpha-beta pruning when applied to Maxent trees. Finally, we present a hybrid algorithm, alpha-beta branch and bound, which combines these two pruning techniques in multiplayer games for more effective pruning. We will also analyze the reduction of an n-player game to a two-player game. Here, let us discuss the e- examples Hearts and Sergeant Major. Heart and Sergeant Major, also known as 853, are both trick-based card games. That is, the first player plays a card face up on the table and the other player follows in order, playing the same suit if possible. When all the players have played, the player who played the highest card in the suit that was led or takes the trick, he then places the played card in his discard pile and leads the next trick. This continues until all the cards have been played. Heart is usually played with four players, but there are variations for playing with three or more players. The goal of Heart is to take as few points as possible. At the end of the game, the sum of all the scores is always 26, and each player can score between 0 and 26. Sergeant Major is a three-player game. Each player is deals 16 cards and the remainder of the deck is set aside. Similar to Hearts, the sum of scores is always 16 and each individual player can get any score from 0 to 16. Now let us discuss max n topic. For a n-player game, a n tuple of scores records each player's individual score for that particular state. That is, for the nth element in the tuple represent the score of nth player at each node in a max and search it. The player to move selects the move that maximizes his own component of the score. The entire tuple is backed up as the maximum value of that node. In a three-player game, we propagate triples from the leaves of tree up to that root. Here we discuss it with the help of example, a three-player max and game tree. In figure 1, the triples on the leaves are terminal values of the tree. The number inside each square represents the player to move at that node. At the node labeled A, player 2 will choose to back up the triple 730 from the left child because the second component of the left child of A 3 is greater than the second component of the right child of A, that is 2. Player 2 does likewise at nodes B and C respectively. Player 1 then chooses a triple from those backed up by player 2. At the root, the first component for player 1's children are the greatest at node A. Player 1 will back this triple up, giving the final maximum value of the tree 730. Now let's discuss duality of maximization and minimization. Since maximization and minimization are symmetric, we briefly present here how the bounds used by pruning algorithms are transformed when we switch from one type of the game to the other type. There are four values we can use to describe the bounds of players' scores in a game. Min P and Max P are players' respective minimum and maximum possible score. Min sum and max sum are the respective minimum and maximum possible sum of all players' score. In hearts, min P is 0 and max P Maxsum and minsum all three are 26. In Sargent measure, min p is also 0 and max p, maxsum and minsum all three are 16. We are interested in how these bounds change when the goal of game is changed from minimization to maximization. The transformation does not change the properties of the game. It simply allows us to talk about games in their maximization forms without loss of generality. The one-to-one mapping between minimization and maximization versions of a game is shown in Table 1. The first row in the table contains the variable names for a minimization problem, followed by sample values for a hearts game, where n, the number of players, is 3. The transformation applied to the values are in the third row. The negation of the original value plus max p min. This renormalizes the score so that min p is always 0. Since hearts and sergeant major are zero sum or constant sum games, max sum is always the same as min sum. The final rows contain the new scores after transformation and the new variable names. The process can be reversed to turn a maximization game into a minimization game. For the next section, my friend Aman will discuss.
Hello everyone, I am Aman Kumar. Today I will explain the pruning in Maxent trees. Pruning basically helps eliminate branches that won't affect the final decision. Each node stores as n tuple of scores for each player in case of Maxent trees. In min max player it will basically store the two value, minimum value and maximum value, but in n tuple it will store the n value in tuple. So in a two-player zero-sum game, there are three types of alpha beta pruning that occur. First one is immediate, second one is shallow pruning, and the third one is deep pruning. Not all of these valid in multiplayer games. Means in multiplayer pruning is very more difficult than in two-player games. Because in two-player games, only the two player is there, so easily to predict the move of other player and what move will affect the other player is it's easy to predict. But in multiplayer games, it is not very much easy to predict the move of other player because so much player is there. Especially deep pruning is mostly ineffective because of course the deeper nodes could influence multiplayers differently. So the first one is now immediate pruning. Immediate pruning happens when a player reaches the best possible score at a node, making further exploration unnecessary. Just like you see in this example, three player is there. So player A will take the some move, then player B will take these two moves, like 10 to 3 is one move and second one is 7 5 1. So for player B, 10 is already getting the best score, so 7 is not the best score here, so we can easily prune this node 7 5 1. So this is the example of immediate pruning. Here the same thing is explained, you can see here in this slide. Second one is shallow pruning. Shallow pruning happens when we can prune a branch based on known bounds at the parent level. Shallow pruning is happening when the sibling node already gives the best score. Just for example, if the player one guarantees 6 points and another move, it's like the sibling move is less than equal to 5 points, which is not giving the best score. So we can prune the other sibling which is not giving the best score. So we will see this shallow pruning with this example. Here the player A is has a tuple greater than equal to 6, and the second one is less than equal to 4, and the third one is less than equal to 4. So the after player 1, the player 2 giving the already the best score like 6 3 1. So after player 1 is sibling, means like player 2 again give like less than equal to 5, greater than equal to 5, less than equal to 5, which is not satisfy the above condition and give the result as 451, which is definitely the not the best score. So we can prune this sibling. So its sibling 631 gives already the best score. So this is the example of here shallow pruning. The third one is deep pruning. Deep pruning tries to prune the node using grandparent level bounds instead of just looking at the parent node. Deep pruning is rare in multiplayer games because future moves might change the game state significantly. Pruning in multiplayer games is still possible, just like immediate, shallow, and deep pruning is still possible in multiplayer games, but it's very much weaker than in two-player game. We will see deep pruning with this example only. Just like you can see here, player A take a move like the first parameter of the tuple is greater than equal to 6, second is less than equal to 4, third one is less than equal to 4. So player 2 is giving already the best score like 730. It's child level. At child level it's give the already the best score, but at the grandchild level it is not giving the best score like 415 is there. So we can prune this grandchild based on its grandparents. So this is the example of deep pruning, you can say. Now the asymptotic result is there. So asymptotic branching factor tells us how fast the number of nodes grows as we go deeper in the game tree. Just like a smaller branching factor means t grows slower, which will save so much of memory, and also we can basically efficiently use our memory. So it's making the game easier to compute. So but in shallow pruning it is not shrink so much the tree. Just we can see its branching factor is 1 plus a square root of 4b minus 3 by 2, which is not shrink so much as this tree. But we can compare this with two-player game. So in two-player game, alpha beta pruning reduces the branching factor to around root b, which shrinks the tree so much efficiently. For example, in Game of Hearts, we can use immediate pruning, but it is very difficult to apply shallow pruning, and especially deep pruning is very much ineffective in this case. So thank you. Next point will explain my friend Sayan Datta. Thank you.
Hello everyone, I am Shayan Datta and I will explain reduction in paranoid two-player game tree. So first of all, this topic discusses a technique in multiplayer game tree decision making, where in multiplayer game tree, as we know, each node represents a game state and the age represents the possible move, the depth represents the number of turns taken to move from one node to another. Here, in multiplayer game tree, as we know that all the opponents are collaborating in each other in adversarial search. To simplify the game tree, two players are taken. One player is the max player, which tries to maximizes their score, and the rest players are known as min players, which tries to minimize the max score. The paranoid assumption refers to the context that in decision tree, the outcomes, the assumption and the outcomes of opponent players optimally to minimize the reduction in the context. Two techniques to decrease the size and the complexity of the game tree to reach the goal node. So specifically, paranoid model is used when there is too many players competing against each other and we need to reduce the complexity and discarding those steps which are not needed in taking the decision. So mostly it is used in decreasing the complexity and also helps in trade-off by making the best strategic decision among the players and not collaborating those which are not used. The next topic is depth first branch and bound technique. It is a technique used in optimization and search adversarial problems where depth first search and branch and bound both are used in combination, as the objective function here is to find an optimal solution efficiently and effectively in minimum time. It is uses mostly of three steps: branch, bound, and pruning. Here the search space is defined, which refers to a given search tree from root node to the goal node, where each node as specified is refers to states and each edges refers to from one edge to another edge move. So branching refers to breaking the problems into multiple sub-problems, which are the child nodes, and bounding refers to use of heuristic function in this case, like especially the monotonic heuristic function that helps in taking those problems whose best outcome is calculated and the rest other outcomes are discarded and helps in finding the optimal solution. These are all NP hard problems, and since the search space is prohibitively large, so mostly local search and exhaustive search are not used. Rather, pruning is used to take only those nodes value whose heuristic is currently best and discarding others. It is of two types: single agent branch and bound, as here explained, and multi-agent branch and bound. Single agent here refers to search algorithm where optimization problems are used to find best possible solution using one particular player or one particular agent. It searches sequentially from one step to another. From one node, it calculates the other nodes and it sells heuristic problems and heuristic values, and from there on it takes only those values which is currently the best and discards the other. Mostly it searches the nodes in sequential manner and thereby finding the optimal solution. Knapsack problem, 01 knapsack problem, traveling salesman problem are used in this type of search. Multi-agent branch and bound. It is also the same step, but here since multiple players involved, so various types of steps are taken and not the best step is taken, like player 1 makes a move, player 2 heuristic value is also calculated, and player 3 in parallel. Since many players are involved, so the complexity increases and parallelly all the steps are checked and only those state is taken whose outcome has the least time. Since single agent and multi-agent branch and bound uses much more time, so it is used in both cases. Thank you. Now Tarun Mondal will continue the next topic.
Hello everyone, today I'll be discussing alpha beta branch and bound pruning, a powerful algorithm for multiplayer games. Alpha beta branch and bound pruning is a hybrid algorithm that combines two pruning techniques to efficiently navigate multiplayer game trees. It leverages both backed-up values from shallow pruning and monotonic heuristic limits from branch and bound pruning to create tighter bound for decision making. How it works. The key innovation here is how it combines information from all players to enable more effective pruning. When one player establishes a score bound from backed-up values and another player's heuristic guarantees a minimum score, we can tighten the original upper bound by subtracting both the values from the maximum possible values. Let me generalize this for a n-player game. For example, if you have a lower bound on player I scored from the parent and player J is playing at the current node, the upper bound on player I can become max sum minus score of J minus sum of all heuristics for all the players except for I and J. By doing so, we can generalize this approach for a n-player game. Performance insights. So this algorithm is not any worse than shallow pruning. Either it performs better in some cases or it performs about the same. This is the algorithm that is followed to realize this idea. If we follow that algorithm, the solution main key point of solving this issue is by subtracting the score and the heuristics of all the players except for the two. Here, for as an example, player 2 will have a 3 backed up value and player 3 will have heuristic value of 2. So player 1 can have maximum minus score of 2 minus heuristic of 3 equal to 5. We can use this value 5 to get the decision whether to prune or not. Here we are pruning. We have experimented with this algorithm for Sergeant Major game, a 3-player card game. We tried for 5 tricks, that is the 5 iterations of the game for 200 random trees. We have found that On an average, the full tree size is about 3.3 billion nodes. After implementing alpha beta branch and bound algorithm, we have reduced the search space to only 1.43 million. By doing so, we have reduced the search space and have got better results overall. Key observations: even though it may seem that paranoid algorithms are better performing than alpha beta branch and bound, it is not true at all, because paranoid algorithms believe that everyone is playing against them, even though that may not be true, making them take harsh decisions and wrong results often. So even though the value of nodes in paranoid may seem lesser, but that is not at all representing the reality of the problem solution space. The future achievements: there are a lot of things remaining to solve. Like multiplayer game still cannot match the two-player alpha beta performance. We have to proceed further and innovate new algorithms to have even better performance. Certain measure like game can be solved for a limited depth, but if the game is too deep, then we may not be able to solve it efficiently or not solve it at all. There is broader significance to AI research for a multiplayer game. There are a lot of different scenarios that simulates the similar kind of situation. Multi-agent system and negotiations, like resource allocation under competition, economical models with multiple stakeholders, coalition formation in political and business context. It is possible to have better solutions if we can develop more and better algorithms like alpha, beta, branch and bound. Future directions of algorithm: we can also combine probabilistic nature to this algorithm. There could be machine learning neural networks to get better heuristics. That we can develop more and more hybrid models like alpha, beta, branch and bound. We can develop strategies for games that is not at all antagonizing against each other, but can but games where often players cooperate with each other or form alliances. While two-player zero games allow for aggressive pruning due to their inherent antagonistic structure, multiplayer games create complex independencies where one player's decisions affect all others in uniform ways. As computational power increases and algorithm becomes more sophisticated, we can expect multiplayer game AI to evolve dramatically. The ultimate goal remains creating algorithms that can effectively navigate the complex social dynamics of multiplayer game interactions while maintaining computational feasibility, a challenge that mirrors many real-life problems where multiple competing interests must be balanced effectively. Thank you.